This is Daisuke Kadoh from Dosho University. So thank you for inviting me to this NumString workshop. And I'm studying tensor renormalization group method these days because TRG method is very powerful to study theories with the sign problem. And today in this lecture, I'd like introduction of TRG to those who do not know this approach well. So I think my talk could be very easy to experts of this field. Anyway, I'll start from talking about the lattice field theory and I'll be explaining what the sign problem is. And the quantum field theory has it has infinite degrees of freedom and has nonlinear interactions in general. So it's difficult to evaluate physical quantity of QFT in general using some analytic method beyond the perturbation theory. And lattice field theory is widely used to estimate physical quantity of QFT with numerical simulations. In lattice field theory, space-time is discretized as a lattice, and fields are defined on sides and links of the lattice. The scalar field and fermion fields are basically defined on sides, and the gauge fields is defined on a link, which is emanated from a side. So in lattice field theory, the expectation value of an operator O is just given by a simple multiple integral. So we can use Monte Carlo method to evaluate the expectation value of lattice field theory. And in the Monte Carlo method, the configuration files are generated with the probability of exponential minus s. And the expectation value is estimated as an average over the generated configurations. So in this method, the action should be a positive real number because it's used as a probability that generates configurations. Actually, the action of QCD is real positive real number. So the Monte Carlo method effectively works for zero density QCD. However, the action of generic quantum field theory is complex. So the Monte Carlo method does not effectively work for general theories. And actually, this problem is called the sign problem. And there are many cases and theories with the sign problem. And as you know, the finite density QCD has a sign problem because the fermion determinant has imaginary part that is originated from chemical potential. And chiral gauge theory and supersymmetric theories have chiral interactions, which are proportional to gamma 5, and such interactions lead to the imaginary part in the fermion determinant, and the theta terms is included in the action as I theta FF tilde, and in the real-time simulation, an evolution operator is expressed as exponential IHT. So these important models and cases suffer from the sign problem. And in order to understand the evolution of early universe and to study the theory beyond the standard model, we can say that it's important to solve the sign problem. And the tensor renormalization group approach is completely free from the sign problem. In this approach, the partition function is expressed as a tensor network, and once the tensor network representation is obtained, we can use tensor TRG method to coarse grain the tensor network, and this tensor network is reduced to a smaller size network. And by repeating this procedure again and again, the partition function is expressed as a single tensor. So we can evaluate the numerical value of partition function approximately from a single tensor. So this coarse graining steps do not have any stochastic process, such as generating configurations with the probability. It does not have any stochastic process. So there is no sign problem in this method from the beginning. And many previous works have been done. Many previous works related to the TRG have been carried out so far. So for related studies, please see the reference of this proceedings of Lattice conference last year. And firstly, let's introduce the diagrammatic notation of tensor network for the later convenience. The rank for tensor T IJKL is expressed as this diagram, and T is expressed as a cross. And these four links correspond to the indices of the tensor. And you can decide how to arrange the index as you like. So I arranged IJKL counterclockwise to correspond to these four links. And the contraction of two tensors is expressed as this diagram. And the T is a rank 4 tensor and S is a rank 3 tensor. And the indices of T K, A, B, C, and the indices of S I, J, K. And the index K is shared by two tensors, T and S. And the shared tensor means that the contraction is taken by this summation, okay? So, and in 2 dimensions, if the lattice theory is defined on 2-dimensional square lattice, then the partition function is expressed as a tensor network on square lattice. And if we assume the periodic boundary condition, and if the lattice volume is 3 squared, these two lines are the same. And these two are the same under the periodic boundary condition. So if the lattice volume is 3 squared, the partition function is a tensor, is a 3 by 3 tensor network. Okay, and each links is shared by 2 sides, shared by 2 tensors, and shared links correspond to the contracted indices. and contraction of index is taken by this summation. Okay, and in 3 dimensions, if the lattice theory is defined on cubic lattice, that the shape of tensor network is also cubic. And the lattice theory has locality and the translational invariance. So obtained tensor network is locally connected and homogeneous tensor network. This locally connected means each tensor is connected only with the nearest neighbor tensors. And homogeneous tensor network means that all the tensors are the same tensor T, because thanks to the translational invariance of the lattice theory. Okay, and I said that the partition function is expressed as a tensor network. The reason why Z is expressed as a tensor network can be easily understood. And in case of Ising model, the partition function Z is given by a product of this hopping term, and beta is coupling inverse temperature, and J is coupling constant. Sigma n is spin variables, which takes +1 and -1. And the lattice size is denoted by n and -1 hat and 1 hat and 2 hats the unit vectors in one direction and 2 directions respectively. So these terms represents the nearest neighbor interactions of the 2-dimensional classical Ising model. And these hopping terms can be written in this form by using Taylor expansion of this exponential, and sigma n squared equals 1. So this hopping term is equal to this form. And so and this form can be written in this form using the 2x2 matrix W. This W, for instance, W10 is this factor to the 0 equals 1. So W10 equals square root of hyperbolic cosine beta j. And so W is 2x2 matrix, which is defined by this function. Okay, so an important point here that is that the sigma n, which is spin variables on site n, is separated from the other spin variables using the new index I. So we can take the summation over spin variables in the partition function. The rank 4 tensor appears by taking the summation over sigma n. And actually, 4 W's come from the 4 links, and 4 W's contains sigma n. And rank 4 tensor is obtained from 4 hopping terms. And after taking the summation over spin variables, this summation over I remains in the partition function, and applying this decomposition to all the hopping terms, partition function is expressed as a product of W. And defining this tensor, the partition function is expressed as a product of tensor, and the new index I is shared by 2W, meaning I is shared by 2 tensors. And the new index I is contracted by this summation, so the partition function is expressed as a tensor network, okay? And so the partition function of two-dimensional Ising model can be expressed as a tensor network. But a tensor network representation is not unique. Actually, let's see another definition of tensor network. And this adding auxiliary spin variables, sigma and prime, to prime and writing the second hopping terms in terms of sigma and prime, the partition function can be written in this form. Of course, the integrating sigma and prime, the dash of second hopping terms is removed under this Kronecker delta. So this form this form gives the partition function of the two-dimensional Ising model, and this part depends on 4 spin variables: sigma n dash.
Daisuke, one question.
Sorry.
One question.
Okay.
Is there a trace missing in this expression? Partition function has to be a number. But I see matrices.
Okay, trace is given by the summation over the spin variable. Trace exponential minus beta h. And this is a classical Ising model, so trace is just replaced by the summation over spin variable. Okay?
Okay.
Okay.
Yeah. Okay.
So and this part depends on 4 spin variables. And rank 4 tensor T, if the rank 4 tensor T is defined from this part, the partition function can also be expressed as a tensor network. Okay. In this representation, tensor index is just the spin variable itself. Okay. So from these 2 examples, we found that the tensor of lattice theory on D-dimensional hypercubic lattice is rank 2D tensor because 2D links are emanated from a site in D-dimensional hypercubic lattice, and links correspond to the index of the tensor, so that the rank 2D tensor appears in D-dimensional hypercubic lattice. And the tensor index is just given by, basically given by the field variable itself. And the tensor components are functions determined by the parameter of the theory. For example, in this case, T1111 equals exponential to beta j. So the tensor component is a function of the parameter of the theory, and the function form depends on the detail of the theory. Okay, so the partition function can be written in the as a tensor network for two-dimensional Ising model. And so we need to consider various issues if we apply the tensor renormalization group method to quantum field theory. For instance, we need to consider how to handle fermions, scalar fields, and gauge fields of the quantum field theory in tensor renormalization group method. And the important models such as QCD is defined on 4-dimensional space-time. So we need to create an efficient algorithm, which can be applied in 4 dimensions. Also, the tensor size becomes large or large internal degrees of freedom. So some numerical approach, such as diagonalization and singular value decomposition, cannot be applied to large size tensors. So we need to create some efficient method to compress the tensor size for large internal degrees of freedom. And there are many issues. There are many issues that need to be addressed, but the difficulty level varies from problem to problem. It's easy to handle fermions in the TRG method, and not so difficult for scalar fields. And the tensor network for U1 and SU2 can be given by using character expansion. However, it's difficult to compute the character expansion for SU3 gauge groups. So we need to make a new method to define tensor network method for SU3 gauge group. And it's a little bit difficult to find a good algorithm in higher dimensions. And I think the most difficult problem is to find a good method, a good TRG method for large internal degrees of freedom. So, okay, so in this lecture, firstly, I'd like to talk about tensor renormalization group method in 2 dimensions. Then we will see the TRG computation for scalar field theory in 2 dimensions. After which, I will be explaining how to handle gauge fields in TRG and how to define higher dimensional TRG algorithms. Then I will be explaining how to handle fermions in TRG method. And if we had time, I will be explaining recent progress, which is an application of TRG to quantum res calculus, which is a model of quantum gravity theory. And finally, I summarize. And the tensor renormalization group method was originally proposed in 2 dimensions in condensed matter physics. And as already mentioned, the partition function of 2D classical Ising model can be expressed as a tensor network. And once the tensor network representation is obtained, we can apply the TRG to renormalize the tensor network. Okay. And the singular value decomposition is used to define a tensor renormalization group. And the singular value decomposition of a generic n by n matrix Tij is given by this form. This is similar to the diagonalization of a matrix, but T is not Hermitian, so we cannot use the diagonalization for T. And for general matrix T can be it can be expressed as this form. And U, V are unitary matrices, and sigma n are called singular values. For the later usage, they are sorted in descending order. Okay, and if we compute TT dagger from this decomposition, using this decomposition, in TT だが U シグマ V、V だがシグマ U だが、so VV だが equals 1 sigma M is squared in TT だが、so the singular values is square root of eigenvalue of TT だが or T だが T. And the unitary matrix U is a set of eigenvector of TT だが and V is a set of eigenvector of T だが T. Okay? And using these two matrix S and S prime, this decomposition can be written in this form, absorbing singular values into the definition of S and S prime. And so the singular value decomposition gives a low-rank approximation of T by truncating this summation up to D. Okay, so the the rank of T is N in general, but the rank of right-hand side is D because the singular values, the summation is truncated. N minus D singular values of right-hand side are 0, so the rank of right-hand side is D. So this rank D matrix gives the best low rank approximation of T because small singular values are discarded in the truncation, in this truncation, but the D largest singular values are included in this truncation. So this truncation gives a good low rank approximation of T. Okay. So once the SVD is given, the tensor, rank hole tensor can be approximately decomposed into two rank 3 tensors, S and S1 and S3. And in this case, the SVD is given by n by n matrix T given for n by n matrix T, and we can regard rank hole tensor as a matrix regarding Ij as a column of the matrix and KL as a row of the matrix. So the other matrix T is D square by D square matrix. If I runs from 1 to D, Ij runs from 1 to D square, so and KL runs from 1 to D square. So other matrix T is a D square by D square matrix. So actually, M runs from 1 to D square, and the summation is truncated up to D. This and so the rank hole tensor is approximately given by this form using the SVD, and this decomposition is applied to the tensor defined on even sides. And even side tensors is decomposed like this, and new index M appears between Ij and KL, and is another decomposition for tensors on odd sides, and the new index M appears between IL and JK for tensors on odd sides. Okay, so, and with the truncation, without the truncation, M runs from 1 to D square. Okay, and this M becomes the tensor index of renormalized tensor. So the bond dimension of renormalized tensor increases without the truncation. However, with the truncation, the bond dimension does not change. With the truncation, the bond dimension is kept fixed up to D with the truncation. Okay, so starting from the tensor network and applying these two decomposition into tensors.
One question.
Okay.
Question.
Okay.
Is there any general rule for determining D cut?
General rule. So the less important information is discarded.
So how do you quantify least important information?
To check the convergence as D increases. So I will show the numerical results later. So we will discuss it again.
Okay. Thanks.
So the initial tensor network is given by this, and the even side tensor tensors are decomposed like this, and odd side tensors are decomposed like this. And dotted lines are new index that appear in this SVD, and all the solid lines are old indices, and we can take the contraction of all old indices. This part becomes rank 4 tensor, and these parts become rank 4 tensor like this. Okay, so I summarize and I summarize the tensor. I summarize these two steps. And firstly, the tensor network is given like this, and T is decomposed into two S's. So the tensor network can be written in a network of S like this. And the normalized tensor is given by 4 S's. So the network of S can be written in a network of T prime, which is a renormalized tensor. Okay. So the tensor network of renormalized tensor T prime is a square lattice network, but the direction is rotated by 45 degrees. But we can repeat this renormalization again and again because this one is a square lattice network. So, and an important point here is that the number of tensor, number of T prime is half of the number of T, because T is decomposed into two S's, and the renormalized tensor T prime is made of 4 S's. So the number of T prime is half of the number of T. So repeating this procedure again and again, finally, the partition function is given by a single tensor whose indices are contracted in it. Okay, so we can take the contraction numerically to obtain numerical value of Z approximately. Okay, so this is a tensor renormalization group method. And this figure shows numerical results of free energy in two-dimensional Ising model. And the two-dimensional Ising model is an exactly solvable model. So we know the exact value of free energy. And y-axis represents the relative error of free energy, and x-axis is temperature. And in this figure, the results obtained from the other methods are also plotted. this curve is the result of TRG, which I explained, and as clearly seen in this figure, the magnitude of relative error is of the order of 10 to the minus 6 or 10 to the minus 7. So very accurate results are obtained with TRG method. So this truncate the less important information is discarded by this truncation, but such truncated information does not affect the value of free energy. Okay, because the relative error of free energy is obtained in this order. So, okay, so very accurate results are obtained, and the truncation effectively works in the tensor renormalization group method. Okay. So I summarize the property of TRG, and the renormalization procedure consists of two steps. One step is decomposition of tensor. The other is contraction of tensor. These two steps do not have any stochastic process. So the tensor renormalization group method has no statistical errors. So there is no sign problem in this method from the beginning. This method effectively works for the theory with the sign problem of the Monte Carlo method. Okay. And the TRG has only systematic error that is originated from finite decut effect. And the Partition function free energy are directly calculable in this method. And the computational cost is proportional to logarithm of the volume time by d cut to some power p, and this power p depends on the renormalization scheme. And the TRG method, in the TRG method, p is 5, but the TRG is only defined on 2 dimensions. In the p is 5 for TRG, and higher order TRG and anisotropic TRG methods are defined on any d dimensions. For those p is 4d minus 1 for HOTRG method, and p is 2d plus 1 for anisotropic TRG method. However, the computational cost strongly depends on the dimensionality. Okay, so we will see the TRG computation of scalar field theory. As I will be explaining what the difficulty in TRG for scalar fields is. As already mentioned, the tensor index is spin field variables itself, and for Ising model, the tensor index takes finite number of values.
I have a question. Yeah, I was waiting for the moment that I can ask the previous discussion on the this lattice. So here you talk about this triangularization of the 2D. So is there also possible to the rectangularize? But can you also do this using the triangularization of the 2D surface and then do this RG? Is it also maybe in principle it's possible, but maybe is there some practical difficulty or?
So did you mean sorry
Here
could you sorry, what is that? What is your question? Could you repeat?
So in this discussion, you talk about this rectangular lattice of the 2 dimension, and then you do that. Instead of rectangular, but what if using the triangularization, like using the triangle to lattice? I don't know the name, but like a triangularization of the 2D surface, and then is it possible also do this kind of?
Yes, it's possible. So the tensor renormalization method can be defined on some honeycomb lattice. The tensor network defined on triangular lattice is expressed as a tensor network of honeycomb lattice. So and the TRG method is defined on square lattice network and honeycomb lattice network. So
is it like a efficiency point of view or like a practically, which one is like a more faster or easier?
It's very difficult question. There are many improved TRG methods. So I think, but no, higher order TRG method is effective in 2 dimensions, I think. So for fixed computational time. Okay. For fixed decay, the other method provides a better numerical results, better performance. But for fixed computational time, higher order TRG method is show better performance.
Okay, thank you.
Can you say what these other methods are, or are you going to describe them later?
Sorry?
You have these other methods, 3 other methods on the graph. Can you describe what they're doing, or are you going to describe them later?
Yes. But I will be explaining HOTRG and SRG method, but I will not explain HOSRG method. I will not explain this method later. But these 2 methods I will explain how to define these 2 methods later.
So, may I ask a question at this point?
Okay.
Am I audible? Could you hear me?
Sorry?
Do you hear me?
Yes.
I have a question about this, what you described from square lattice. You're going from this 4-rank tensor to 3-rank tensor in even and odd sides. But that, I suppose, is arbitrary, right? We could choose to decompose the other way for even and odd sides. From what you did, it presumably gives the same result. Can that be argued?
Yes, but the error is the relative errors are different, but converged result, the same converged results are obtained.
Okay. And I have another question. Maybe you could answer it later if you prefer. Could you explain exactly in coarse graining which degrees of freedom are being integrated over if I compare with standard RG in this approach? When we go from a smaller lattice to a larger lattice, which is this 45-degree rotated, and repeat this step. At each step, which degrees of freedom of the original theory are we losing or integrating over?
Original degrees. It's a very difficult question. So let's discuss it later. But I'm joining the workshop remotely. So please email me. So
okay, sure. I am also joining remotely. I just wanted to compare with the normal RG, how to understand this approach compared to normal RG. I mean, Wilsonian RG, I mean.
Yes.
Thank you.
Okay.
I mean, qualitatively, I can tell you, he's summing out degrees of freedom. So he's changing the lattice spacing by, I guess, the square root of 2. But the difference is usually in RG, you introduce longer range couplings. In this case, you introduce a tensor structure on each site, right? So it's sort of like the difference between a lattice version of operators versus taking higher derivatives of an operator's site, okay? Those are two ways to introduce more operators, okay? But in this case, the new operators are always at the same site, right? So, I mean, it's different, but that's the difference. Yeah.
So,
Thank you.
And so, the tensor index takes a finite number of values for Ising model. However, for scalar field theory, tensor is infinite dimensional tensor because tensor index is scalar field, which takes any real number for scalar field theory. So we need to discretize scalar field to define a finite dimensional tensor. Okay. And Gaussian quadrature rule is used to discretize one-dimensional integration. And this one-dimensional integration is approximated by this summation in the Gaussian quadrature rule. And this summation is taken over k discretized point. And gk is a weight function. In case of Gauss-Hermite quadrature, the discretized points are a set of 0 points of k's Hermite polynomial. And the weight function gk is given by this. And k is the order of approximation. And the efficiency of this approximation depends on the function form of f. If f is exponentially damping function for large phi, the Gauss-Hermite quadrature effectively works. And for the scalar field theory, each path integral measure of scalar fields is replaced by summation over k discretized point obtained by the Gauss-Hermite quadrature. So by using this discretization, phi takes k discretized point. So after this discretization, the hopping term of scalar field theory is just a k by k matrix.
Daisuke, one question.
Okay.
On the previous slide, so this Gauss-Hermite quadrature is one of the several formulas available for this, right? Is that correct?
Gauss-Hermite quadrature works if the function has exponentially damping factor. In scalar field theory, lambda phi 4 interaction provides exponentially damping factor. So I think this method effectively works in scalar field theory, but other Gaussian quadrature such as Gauss-Legendre or something like that does not work for scalar field theory.
I see. Okay, thanks.
So after discretization of scalar field, the hopping term becomes a k by k matrix. So once the k by k matrix is given, we can use the SVD of the matrix like this. And phi n, the phi n is separated from the other scalar of the other nearest neighbor scalar fields. So we can integrate phi n to define tensor. Okay, so the partition function is given by a product of this hopping term, and integrating phi n, the partition function is given by a product of tensor whose indices are contracted by this summation. So the partition function of scalar field theory can be written in a tensor network, whose tensor is d by d by d by d tensor, rank 4 d by d by d by d tensor. Okay. So, and this action is two-dimensional. This action is this action is the two-dimensional real Phi-4 theory is given by this lattice action, and M0 and lambda 0 are coupling constants, and the continuum limit of this theory corresponds to lambda 0 to 0 limit, and this action is invariant under G2 transformation. This G2 symmetry is dynamically broken. So the critical coupling constant, we study the critical coupling, the value of critical coupling. We evaluate the value of critical coupling constant using the TRG calculation. And using the discretization of scalar fields, the partition function can be approximately given by a tensor network. So once the tensor network representation is obtained, we can apply the TRG method to evaluate the value of free energy. And this figure shows the susceptibility obtained by the TRG method. And the susceptibility shows the susceptibility obtained by the TRG method is on this straight line, which corresponds to this formula. And from this results, the critical exponent is obtained critical exponent is consistent with that of two-dimensional Ising model, and critical mass is obtained from the fit of this data. And this figure shows a critical coupling constant, and this line corresponds to the continuum limit, and these red points are the results obtained from the TRG method. And our results is consistent with those obtained from the other method. So we can say that the discretization with Gauss-Hermite quadrature properly works. Okay.
You know, the in this lattice model that you put down, there's a critical surface for all values of bare coupling. And in fact, the Wilson-Fisher fixed point is usually the place one runs at. You don't have to go to the continuum limit to get the right CFT and exponents. So do you try that? I mean, there's two ways to get to the conformal field theory. There's a whole critical surface, and lambda is actually irrelevant. So one way people do it in Monte Carlo is they actually do totally the opposite. They go way up to strong coupling to get to the Wilson-Fisher fixed point.
Mhm.
And they fix the bare coupling and only vary the mass. It's true you will not get the continuum field theory, but you get this. You get the right CFT. So I'm asking, can you do this without scaling lambda?
Yes, so but in this figure, we just evaluated the critical coupling constant from this.
What I'm saying is there isn't a critical coupling. It's irrelevant. The only relevant parameter is the mass.
Yes.
You're going to go to CFT.
Yes, I think, yes.
So what happens if you fix bare lambda? Can you get the theory? That's certainly what you can do in the exact theory. You do in Monte Carlo, you can see that there's a critical surface. There's only one critical parameter. That's the mass.
Yes, yes, yes. So by tuning the mass at the critical point, the continuum limit is obtained by taking lambda to 0. So
no, sorry, that's not the only way to do it. In fact, lambda goes to infinity in a double well potential becomes the Ising model, which is the same critical theory. I'm saying getting to the critical theory, you can get it in different ways. It's not that what you're doing is not true, but you can fix lambda bare, any value actually, and the optimal value is actually to be close to the Wilson-Fisher fixed point. That's the fastest convergence for the partition function sampled by Monte Carlo. So I would think that you would try to get close to the Wilson-Fisher fixed point and not scale lambda if you wanted to only get the conformal field theory.
Okay. Okay. So, okay. But okay. But the other.
But I would wonder why it wouldn't work that way. I mean, it certainly works that way for the partition function when evaluated in Monte Carlo. We know exactly where the Wilson-Fisher fixed point is for your action.
Okay. Anyway, we can. We want to check the discretization properly. We want to check if the discretization properly works. So
I'm sorry. This gives you the exact critical theory
consistency between among other methods. So
just another route to the same thing. I'm wondering why that wasn't tried.
Okay. Okay, so anyway, the discretization itself properly works. So by using the discretization method, the to decompress fiber theory is also discretized. The scalar field, compressed scalar field is also discretized by using Gauss-Hermite quadrature. And this acts the 2D complex fiber theory at finite density is given by this action m squared, m and lambda coupling constant, and mu is chemical potential. And this model has a sign problem at finite chemical potential because there is a pure imaginary part for non-zero chemical potential. And the theoretical prediction tells that the bulk observables, such as particle number density, are dependent of the chemical potential, which is less than some critical value. So this phenomena, this is called silver braid phenomenon, and which is closely related to the imaginary part of the action. Without the imaginary part of the action, in the phase quenched theory, silver blaze phenomena cannot be observed in the phase quenched theory. So we need to treat the imaginary part of the action carefully to observe the silver blaze phenomenon. And this figure shows a particle number density obtained by the TRG method for various values of lattice volume. And for V is 256 squared, the silver blaze is clearly observed for large volume lattices. And also, for the expectation value of phi squared, results similar to the number density are observed. So, and this figure shows average phase factor. And average phase factor measures the severeness of sign problem. If the average phase factor is 0, this phase takes -1 and +1, and the phase is fluctuating from -1 to +1. So for large volumes, the average phase factor is mostly 0. But the silver blaze phenomena is clearly observed by the TRG method. So I think the TRG method properly works for the theory with severe sign problem. And this figure shows a particle number density. These green curves is the particle number density obtained from the phase quenched theory. The particle number density of phase quenched theory does not show the silver blaze phenomena. So the silver blaze is closely related to the phase of the action. And comparing these two results, the TRG method properly works for field theory with severe sign problem. Okay, and okay, so I want to stop my talk here because here is a good spot to finish my talk, because the new story begins on the next page. Okay, thank you.
Thanks, Daisuke. It's also a good time to finish the talk. That gives us another 10 minutes or so for any further questions or discussions that we have on these first two sections of the formalism and the generalization to scalar fields. So are there any further questions or comments about what we've seen? Behind me.
So on one of your slides, you had this scaling law with logarithm of volume and the d-cut. So
Yeah.
Can one understand this log volume part? And also
the number of renormalization steps scales with the logarithm of the volume, because the number of tensor is reduced in half per one renormalization step. So the number of renormalization step is proportional to logarithm of the volume. The number of tensor is reduced in half per renormalization. Okay, so the number of renormalization steps is proportional to logarithm of volume.
And how does it scaling compare to this matrix product states, which are also similar?
I've never tried to compare the scaling, so I'm not sure.
Okay,
Hi. When you mentioned the design problem, you also mentioned about this real-time formalization, Schwinger calculation.
Yes.
And here, I think you mostly talk about this Euclidean, but can this method be used in the real-time for Schwinger calculation formalization? Or
Yes. Yes, we can use TRG method to study Schwinger calculation formalism, but in that case, exponential I lambda phi 4 terms appears in the appears, but in that case, the discretization of scalar fields does not work because exponential I lambda phi 4th is not a damping, exponentially damping function. So to study, to use TRG method to Schwinger calculation formalism, phi, we analytically we perform analytical continuation for phi, so that the exponential I lambda phi can be written in exponential minus lambda phi fourth, phi to the fourth. So after the analytic continuation, we can use Gauss-Hermite quadrature for the Schwinger calculation formalism of scalar field theory, and such treatment can be such treatment is studied by Shinji Takeda, and so please see his previous paper. We can use TRG method to Schwinger calculation formalism for scalar field theory. Okay.
I see. So just to make sure, I mean, when you discretize now, this is real time. So you also discretize space-time, both space and time, or you just discretize spatial coordinate, or
the spatial what do you mean? The space-time is discretized by lattice.
In usual Euclidean, but in Lorentzian or this kind of real time, do you also describe both time and the
discretization of time is needed.
Yeah. Okay, I see. Thank you. Yeah, that's my case. Just simple question. Yeah, thank you.
I have a naive question about the decut estimation. So it appears like a dimensionality reduction or a data compression problem, is it?
This dimensionality comes from the contraction, the number of contraction of the cost of contraction of two tensors. The tensor, the rank of tensor is proportional to 2D in D dimensions. So the cost of contracting two tensors scale with D to some dimensionality. Okay. Because the rank of tensor is proportional to D, 2D. So two tensors of rank 2D costs expensive, and the cost is proportional to D to the D.
So like how efficiently we can compute this decut value. So there are some methods, some machine learning methods, some methods applied in machine learning like PCA, this principal component analysis, which can compute like up to what standard variance you would want to compute these values. Like one can compute a covariance matrix of these tensors, and from there, what the limit of the variance one can estimate these limits or cuts on the matrices or tensors. So do you think something like that can be applied here as well?
I don't have any idea about that point. So
yeah, so it appeared to me like it's more of a data compression or reducing the dimensions of matrices a problem. Okay.
yeah,
Thank you.
the problem is very similar, but
since complex actions aren't a problem for you, it looks like you should be able to apply this method to Minkowski space rather than Euclidean. Is there an obstacle?
sorry.
To actually do real time
Yes.
as opposed to Euclidean time.
We can use TRG method to real time.
And has somebody done it?
Yes. The Shinji has already done the real-time simulation of scalar field theory using the Singer-Keldysh formalism.
Your last transparency on this chemical potential, I just like to understand it better. So you're fixing lambda, is that the bare lambda you're fixing at 1?
Yes.
So you fix the bare lambda, and then
Yes.
you're not at the critical point, so you have massive states. Is that right?
Yes, but the
So
test.
let me give you my interpretation. Tell me I'm totally off the beam. So what's happening is you have massive states. You're not at the critical surface, right?
Yes, but as a test.
Right. So then the chemical potential has to give you enough negative energy to be able to produce these massive states. Is that why you're getting this kink? The chemical potential is trying to produce states, right? I guess what I'm wondering is what does this 0.9 mean? And is that universal in some sense, or does it depend on the mass that you give the states?
Yeah, well, I've never tried changing the parameters as a test.
Let me put it this way. If you're not on the critical surface, then you don't have massless states, right? So you have a gap before you put the chemical potential in, right? If I take a theory off of the 5-4 theory, the Ising model has massive states away from the critical surface, right? So as I understand, you fix lambda and you're not, before you put in the chemical potential, m squared is not on the critical surface. Is that correct?
I think it's correct.
So now you have massive states and it's a multi-body system, and now you push the chemical potential to try to create those states, right? And clearly you'll start to have an explosion as soon as the chemical potential can compensate for the mass of the states, right? But then I would think, so my confusion is, then I would think 0.9 would depend on the value of the mass. Does it? Yeah, the renormalized mass, the actual mass of states. But
that's the renormalized mass. That m squared.
Well, I'm just asking the question. If you change mass squared from 0.01 to 0.02, would be a critical change?
This is my project.
That's my question.
Yeah, we tried changing the mass parameter, but I forgot the results for different.
Maybe we can revisit this in the second.
Does anybody know? I mean, I would assume that's what happens.
It sounds like a reasonable argument for me, and maybe Daisuke has 2 more lectures on Thursday and Friday and can look up the answer and tell us.
Okay.
I think we've come to the end of the time for today. So let's thank Daisuke for. Thanks, Daisuke. We look forward to hearing more from you on Thursday.
Okay.
We'll reconvene at 2:30 Indian time for research talks after lunch.
Okay. Thank you.